if the upper limit of the integration interval approaches infinity and the integral converges to a finite value, then we can define an improper integral over the infinite interval. Let's try this with a function e to the minus x squared. So this function has a well-known exact value, which can be obtained by symbolic integration. It's square root of pi over 2. Now let's convert this function to a function handle and invoke the function integral to compute the integral in the infinite interval from 0 to infinity in line 82. We get a numerical value, an approximative numerical value with relative error, which is very small, about 3 times 10 to the minus 16. Now let's try the same approach with a different function, namely sin x over x. Symbolic integration gives a value of pi over 2 for this integral over the infinite interval from 0 to infinity. If we convert this to a function handle, gh, we can again invoke integral to get a numerical approximation which gives a warning. Obviously, this does not work very well. You see the symbolic value is pi over 2 and integral returns 3.45, which is totally wrong. There's a huge relative error, more than 100%. So this obviously does not work. So let's replace the upper limit of infinity by a large upper limit, let's say 10 to the 5. And in this case now we get a reasonably precise approximation of the integral with a relative error of 6 times 10 to the minus 6. We can also integrate functions that have a pole in the integration range. So a point where the function value approaches infinity. Let's consider the interval from 0 to 2, and we integrate 1 over square root of the absolute value of x in this integral. Let's have a look at the graph of this function. Symbolic integration works without a problem in this case, and the exact value is given by the value stored in isymb, which is displayed in the command window and also here in the editor window. I convert this function to a function handle, and I plot the graph in figure 2 on the right hand side. The function looks approximately like this. Of course, there is a pole at 0. Let's label the axis, give a title, and I've set the scale in y to logarithmic, so it looks now a bit different than before. Now let's try the trapezoidal room, first with 100 points. It works, but the relative error is large. It's about 4.3%. Let's try 10,000 points with the trapezoidal rule. The error does not change that much. Obviously, the trapezoidal room is not a good choice for this type of function. So let's try quad, which doesn't work at all. It tries to evaluate the function at 0 and then returns none. So this is obviously not working. So let's try integral. And integral works with a relative error of about 5 times 10 to the minus 7.